Known in the USA as shielded metal arc welding, or SMAW, and elsewhere as manual metal arc welding, or MMA, this welding process is by far the most widely used, especially for short welds in production, maintenance, repair, and construction in the field. Welds can be made in areas of limited access, and the equipment is relatively simple, inexpensive, and portable. Welding in any position is possible, provided appropriate electrodes are chosen. The process may be applied to the most commonly used metals and alloys, such as carbon and alloy steels, stainless steels, copper, nickel, and their alloys. It's not suitable for low-melting metals such as tin, lead, or zinc, or the more oxygen-reactive metals such as aluminium, titanium, and zirconium. The specification of welding positions is important for two reasons. First, the manufacturer needs to define the positions for which his electrodes are suitable. Second, the welder's skills and qualifications are to a large extent determined by the position at which he or she can produce an acceptable weld. So, much greater skill is required to weld in an overhead position as compared with a flat or downhand position. It should be pointed out that the welding position is not limited by the process itself, but by the size and type of electrode. For downhand welding, particularly with heavy electrode coverings, the tip of the electrode can be dragged lightly along the joint. The arc length, in this case, is automatically determined by the depth of the cup at the tip of the electrode and the melting rate of the electrode. For vertical or overhead welding, the arc length is always gauged by the welder. The proper arc length in such cases is the one that permits the welder to control the size and motion of the molten weld pool. The same is true for the root passes in groove and fillet welds. Tables are available as guides to the approximate currents to be used with various types and sizes of electrodes, although the actual values used will depend to a great extent on the work to be done. Generally, the higher the current in the range given for a particular electrode size, the deeper the penetration and the faster the rate of deposition. Too high a current can lead to spatter and undercutting, but too low a current will result in insufficient penetration and too small a deposit of weld metal. As a rule, the arc voltage will be observed to increase slightly with increase in electrode diameter. The arc length is the distance from the molten tip of the electrode core wire to the surface of the molten weld pool. Proper arc length is important in obtaining a sound welded joint. Metal transfer from the tip of the electrode to the weld pool is not a smooth, uniform action, and instantaneous arc voltage varies as droplets of molten metal are transferred across the arc, even with constant arc length. However, any variation in voltage will be minimal when welding is done with the proper amperage and arc length, which requires constant and consistent electrode feed. Too short an arc will be erratic and may short-circuit during metal transfer. Too long an arc will lack direction and intensity, which will tend to spatter the molten metal as it moves from the electrode to the weld. The spatter may be heavy and deposition efficiency low. Also, the gas and flux generated by the covering are not as effective in shielding the arc and the weld metal from air. The poor shielding can cause porosity and contamination of the weld metal by oxygen or nitrogen, or both, and the quality of the weld will be poor. At high temperatures, hydrogen, unlike oxygen and nitrogen, doesn't form any compounds with iron and has a high solubility in the austenite phase. Hydrogen has a lower solubility in steel after transformation at lower temperatures on cooling. This hydrogen will cause embrittlement in steel. In a weld and in the surrounding regions, the presence of hydrogen will also increase the tendency to cracking. It's important in all critical structures to keep hydrogen to a minimum. The problem can be minimized by using basic coated electrodes, which have been baked in manufacture and subsequently kept dry. Here the coating consists of calcium and other carbonates and fluorspar bonded with sodium or potassium silicate. In the heat of the arc, the carbonates dissociate, releasing carbon dioxide, which acts as the shielding gas. To further reduce moisture content, they're frequently baked immediately before use. Low hydrogen electrodes are normally tested to demonstrate a weld metal hydrogen content of less than 15 cubic centimetres per 100 of deposited metal. MMA welding is often used for applying surface layers to metals to improve their resistance to abrasion, impact, corrosion and heat. The advantage of this method is that the surface can be deposited on a cheaper base metal to give wear resistance or other qualities exactly where required, with great financial savings. Also, worn parts can be built up with substantial reductions in time and replacement costs. Very hard surfaces are normally required for good abrasion resistance, but high hardness values are usually accompanied by poor resistance to impact. Conversely, good impact resistance is not allied to extreme hardness, and it's therefore necessary to determine which quality is of greater importance. Similarly, consideration must be given to the requirements of corrosion and heat resistance, and to the composition of the base metal, the need for preheating, and the possibility of post-weld heat treatment. The stellite series of alloys, which may be nickel or cobalt-based, are well known for hard-facing applications, which may include caterpillar tracks, excavator buckets, railway points or rock crushers. Cutting tools for lathes and milling machines can be made by depositing a layer of high-speed tool steel onto a shank of lower carbon steel.